All right, so welcome to the session. We're going to go over a lot of concepts today. We're going to go very quick. The idea is that we want to explain these simply. Here's a little show full of what we're going to go over. So we're not going to have much jargon, we're not going to have much code, we're going to try and explain these very simply so it's nice and easy to understand. So a bit on this session first. This is going to be a high-level overview. It's going to be very low technical, right? We're not going to have any code, we're not going to have any demos. We're just going to explain what things are in an easy to understand way, even if you don't come from a super technical background. Now, a bit of data background might help, but other than that, we're going to be really simplified concepts. Now, we might be quite high level and they might be a bit simplified and not always exactly how things work under the covers, but we want to get over the concepts and what's going on. So, firstly, let's have a look at databases. So what is SQL Server? SQL Server, right? SQL is a programming language, this SQL, which is often pronounced SQL, and it stands for Structured Query Language. We use it to return data from databases. And so what is SQL Server? SQL underneath uses a relational database. What this means is that we have tables and they're related to each other. In this instance, by the sales ID, we have name and sales ID of salespeople, and we have what they sold in a different table. Now, there's many types of SQL databases and options. SQL Server or by Microsoft, there's Oracle, and some others, MySQL, PostgreSQL, things like this. We also have a lot of NoSQL. These are called graph, documents, key values, right? Different ways of storing data. SQL Server, though, is an option from Microsoft that stores data in tables in a relational way. So what is serverless SQL? Now we can break down a SQL Server into these kind of different areas. So we have the SQL Server, and this is kind of the house and the power that powers everything. Within the server, we have different databases, and these may be logical ways of storing different information, such as a finance database or an HR database. Within the databases, we have different types of tables. Now, these all run by the power of the server, which is the engine behind it. Now, typically, this used to be on-premise, we'd say. So what we would have is when we pay for this, would set up the SQL Server, would be actually something we had, some hardware. We'd have to store the data and pay for the maintenance. Then, as we went, it got to the cloud. What this really meant is it's just stored by a vendor, such as Microsoft, and then they just charge us for the storage we use and the compute. So in the server, we have the databases which hold the tables. We also have something called serverless, where we don't actually pay for the storage. We just pay for the usage, the compute, instead of databases. Now, obviously, we'll pay a bit more for each compute. The idea is we're not paying for the underlying server or any of the storage costs. What is ACID? ACID is an acronym to describe some items of databases. Now let's look at this example. We have my account and my store's account, and these are transactions I've made. So what's going to happen is I'm going to buy something from the store. So in order to do this, we're going to send two bits of information. The first is say, hey, I'm going to spend $200. So on this date, I'm going to take $200 out of my account. And then it's going to add it to my store's account. Right? So there are two different items, two different transactions. Now, what would happen, for example, if something happened during this? And let me say I took $200 out of my account. Now, the bank processes this, right? The bank owns these tables and they're doing these transactions internally. Before they could run the next statement and say, add $200 to my store's account, there's a big power cut and everything goes wrong. And the bank doesn't know what was going on because everything shut down. So now when they reboot, the system's going to say, I have $200 less. And the store doesn't get that $200. So I'm going to be very annoyed and the store's going to be very annoyed. So ACID is an acronym which helps to stop items like this. And the first letter in it is automaticity. So this means that all statements take place or the transaction doesn't happen. So we call this a transaction, right? So two statements, take $200 in my account, put it in their account. And this is all wrapped up into what we call a transaction. So everything has to happen, otherwise nothing can happen at all, right? We can't have just one of them happen, take it out my account and not add it to the other account. Consistency. This just says everything must be the same before and after this transaction, right? Which is all these different statements that run. Also, we have database rules such as saying, this has to be a currency column, this is a data column, they must be observed. And then the amount of money in this example, $200 couldn't have just disappeared from the system. We need to stop that happening. This is very important. Isolation. We can say, no other processes can happen at the same time. Now, if you look at my account, right, these are the transactions. So I added $1,000 to my account, I spent 100, which means I have 900 left. Let's say we do this again, but it doesn't really matter which way around. So let's say we add the $200 to the store's account because we know we're going to debit it from my account. But I'm also doing a separate transaction. Now, first action is that they add the store's 200, but in this separate, I actually buy something for $800. Now we can see we add this up. I only have $100 left in my account because these two things happen simultaneously. This green one kind of slipped between the two transactions here. And this means I don't actually have enough to pay for this. So obviously this is a big issue. So no other processes, right? This has to be isolated from others, so they can't mess up things happening at the same time. And lastly, durability. This just means that we need things to be permanent. So once this has happened, you need to, write it to a disk, store it permanently, so if there's a power cut in the future, it doesn't undo everything that's happened. Now on to the Lakehouse series. So what is a data lake? We talked about SQL Server before, and this is basically a data warehouse, right? It is in SQL. We can build these data warehouses with lots of different databases, and it's called structured. What that means is we have tables, and in this table, we have a name column of sales and a cost, right? And this sales has to be a number. It won't let us put dates or names. This is what I mean by structured. We have rows and columns. Everything's got lots of rules. What about other formats? Right? Now we do a lot of machine learning. Think about all this generative AI and all this, right? It has to look at a lot of different pictures. And then it looks at music, and you can do AI and music and sounds. And then streaming data coming in different fast. And emails and things that don't really have a specific format. So what happens with all of these? Well, simply put, we put them in a data lake. All a data lake is just a big storage container, right? Where we can dump all this stuff in, and it doesn't matter what format it is. So a data lake, right? We can call this structured, and this other stuff we call semi-structured or unstructured, right? That doesn't really have a structure. And we like this because it's good for data science. Data science needs all the data. They don't really care about it being in a nice tabular format. They want to run experiments and find out information. Big amounts of data, right? Because we can add lots of in. Storage has got really, really cheap. So that enables these data lakes just to dump a lot of stuff in. And it's very quick to load data in. Imagine if we have a structured where we have to have things in a table. We have to make sure the data is in the right format, so it goes through a lot of transforming. This way we just save things. It's like a folder that we just save everything in. So what is a data lake house? So a lake versus a warehouse. First, let's look at a data lake. It's good for data science, big lots of data, quick, structured and unstructured. A warehouse is good for business intelligence, right? And other kind of transaction and people that use that. It has ACID compliance. This is that acronym, and strict data validation. However, what we want to do for Lakehouse is we simply combine the best of both. So we want to have this system where we can have lots of different types of data, structured and unstructured. We also want to be able to do things like ACID compliance and make sure that the data has some sort of rigor to it as well. We want to take the best of both worlds and simply just combine the names, right? A data lake and a data warehouse, so a data lake house. Medallion architecture. So one question we have when building a data lake house is how do we make this rules? So one thing is we do architecture over the top. So let's imagine we have this bit of information come in, this table. The first thing is we just save this data raw as it is. And you can see here that this sales ID is clearly wrong. There's some missing data here in this data formats. So we save this raw data. The next step is just kind of clean it. So what we do is we get rid of that bad data, we filter out the blanks, we fix the data, we just clean it so it's cleaned and ready to go. Then the third step is we do some aggregations. We might make some dimension and fact tables if you're familiar with star schema. Basically just means put them into things that are good for reporting and other things that we can use for our end users, business users can use. We've got profit here, we can bind some other information, made some aggregations. We have these three things, and this comes from a company called Databricks, really termed this terminology. You might see them other stuff. So first we have the bronze layer. This is raw data. This is where we just save all the data, we just dump it into the data lake. The next thing we have the silver layer. We validate the data, we deduplicate it, like get rid of the blanks. So we know that the data is correct and doesn't have any errors. And then we refine it and we make sure, and aggregate it. So we do things like calculations and the gold layer. This is good for giving to business users and letting people do business intelligence on top. Delta series. So the first thing is, what is column and row store? Now, column and row store is just how a computer stores information. So imagine we have a table, we have this name, sales, and cost column. In a row store, a computer doesn't store things in a tabular format like that. It likes to store everything in a long line. So what it does is it actually just rearranges it like this. And say, this is row number 1, right? Bill had 9 sales and 6 cost of goods sold. Row number 2, row number 3, row number 4. This is typical in what we call comma-separated values, a CSV value file. You probably had one of these. This is right. It just separates each value by a column and stores everything in rows. Now, what happens if we want to do some analytics on this? This is really good if we're just adding data, adding a row at the end, because it's easy just to add a row to the end. What if we want to select the name column, which is often when we do analytics, we select columns, right? We'll say select the name column. Now you can see this, all that data is quite far away, and it's all spread out throughout the data if we just want the names. Now, because it's spread out, that means that the computer is going to have to spend more time looking for this data. So the data is far apart, it's going to be harder for it. So what we can actually do is we have something called a columnar store. So instead of storing it row by row, it actually stores the data like this in a long line. But now this is column 1, this is column 2, and this is column 3. So it stores it in columns. And what's good about this is we can actually say, hey, I want to select the name column. All this data is right next to each other, so it's nice and easy for the computer. So let's see about optimizing the column store. Now, we see a number here. If I was going to say this number, I probably wouldn't say 3. I would say something like 10 3s, 5 5s. Computers are the same. Computers will run on memory and storage, so at the most it can reduce things, reduce memory, make things more optimal, the better. So a computer could actually say this, 10 3s, 5 5, something like in a way like this. And you can see this third bullet point actually takes a lot less space than the first bullet point, which means it's optimized, it has the same information. So how does this work in a table? Well, we have a table here, and you can see that some of the values are repeated over and over, right? Of course, if we're looking at columnar store, we can think of each column individually. Because we're storing it as columns, everything can be done on each column individually, and this is a big advantage of columnar store. So here we have Bill. Bill repeated 3 times, right? Jane repeated 3 times. So what we can do is every time we get a new value in the column, we just put a number here, 3. So this says, this is Bill, a new value, it's going to be 3 times. This is Jane, this is going to be repeated 3 times, right? Sarah and Alice are repeated once. You can also do this with the client, right? This first one's repeated twice and the second one's repeated twice, so on. Now, if we look at this bit of data, everything without a red number to it is actually redundant, right? Because in this name column, the second Bill, I know that's going to be Bill because I've said that Bill is repeated 3 times. So if we remove this, this still shows the exact amount of information. We can infer what they look like, but without having to have the information actually saved. So that's what it does. It simply removes this, and it stores it in a kind of much nicer way like this. So this is a much more compressed format. And so we've got rid of a lot of rows, which means we've compressed this and optimized the storage. Now let's have a look at this column. Another thing we can do is we can actually say, okay, there's a lot of letters here, right? And if you think every character is going to take up space because we have to store. So I've counted, there's 137 total characters in these 5 rows here. And that's all the letters that make up all of this. What we can do, we still have some repeated values, right? We can see the top and the last column are the same, the second and the fourth column are the same. So if I just say, let's just take a distinct list, a unique list, and just say all of the different values once, and then give it a key, just 1, 2, 3. And I can actually replace the values in my column with this key. So you can see this top value, Lutegan, and this bottom value are the same, and this is number 1. And I replace this with a 1, and the chronin is a 2, and I replace the chronin with a 2. And now, this still says the same information because I can look up the 1 and see what it actually references in my top table. But in this time, I've actually reduced it from 137 to 84. It's quite a big reduction in number of characters. And if you can imagine, this is only 5 rows, but when you have millions and millions, this is a huge amount of storage. So let's have a look. What actually happens going from our table throughout the end is, firstly, we split this down, we remove the unnecessary, we add a bit of information, just say how many times it's repeated. Then, for both columns, right, we do the same thing. We add a lookup table and remove all the letters, so it makes it a lot more efficient. And then as it's stored, column storage, just like we did before, we put it all in a line and column storage. We can see just how, this is quite much smaller, very optimal, and we've really optimized how this column storage is done. So what is Parquet? Parquet files. Now imagine we have a table that looks like this. Parquet is essentially a columnar store file. However, there's one extra little thing it does. Instead of just storing every bit of information in one huge file, it just splits it out into what they call row groups. So in this case, we're going to split the first 2 rows into one group and the second 2 rows into a second group. In reality, these will be much bigger with much more rows, but just to see what happens is we store it like this. And as this is a columnar store, both of these are stored in a columnar format. So again, this is column 1, split over the 2 files, column 2 and column 3. And then what it does is this is actually just stored as files. So I kind of like to think of these as just text files that's stored in a columnar way. And instead of just storing one big table into one big file, it splits it out. And obviously you'll have probably quite a lot of these, right, as your data gets big. So Parquet. So the good thing is it's an open source format, right? So that's why we get a lot of use, because no vendor owns it. It's an open source format. I like to call it a hybrid column-based storage. It is column-based, but it does this thing where it splits the rows out before and makes it into lots of different files. Again, great compression available because of the ability to compress columnar store. It has really good compression. It's better at OLAP, which is analytical processing. This is when you're doing things like looking at columns individually, right? Especially when you're doing analytics, I might say, I want to select this column and this column, rather than OLTP, which is transactional. And this is when you're adding rows. So if you're adding rows and not really looking at columns, probably a row storage is quite good. But generally when we do analytics, we want to look at columns. We want to say, I want to sum the sales column and break it down by the customer, something like that. One of the big downfalls though is you can't edit Parquet files. You don't really edit them. All you can do is delete the Parquet file or add a new one. So this is kind of has a big impact here and makes it hard to store in a great database. We lose a lot of that formality and the niceness that databases provide because we can't go around editing. If I want to change a line, it's very difficult. So what is Delta? So Delta is data that is stored as Parquet files, but it has one big difference. It adds this thing called a transaction log. So Delta is Parquet with a transaction log. So what is this transaction log? Now imagine I have this table and I'm going to save it as Delta. So the first thing it does is it saves it into Parquet tables, to Parquet files. And again, we split this into our row groups. We have file A and file B. And then at the bottom, we have this transaction log. And so what we do is we say, we've written down what we did. What we did is we added these 2 files. So I've added file A and I've added file B. Now I'm going to say, I want to change a row. Right? I've realized Laura, that's not correct. Actually, the value I want is Alice. So I'm going to delete a row of Laura and add a row called Alice in. Now, as we said, we can't edit Parquet files. So what we have to do is, we say we want to do that. It translates it and says, okay, I'm going to add my new file. So I'm going to add file C, which has this bit of information updated, right? So this is my new file in with my new bit of information. and I'm going to stop using file B. And that's what task 2, I write down this, I say adding file C. However, it doesn't delete file B. In my transaction log, I've got task 1, task 2. Task 1 says use file A and B. Task 2 just says, actually don't use file B, use file C. So if I read through the tasks, I can see that, okay, I need file A and file C, and this gives me the most up-to-date information. Now I want to get rid of the row Alice and add Sarah instead. So I write this down, I say task 3, so this is saved a new file to the storage, new Parquet file called file D. And task 3 says, don't use file C anymore, but use file D. Now file B and file C are still there. Each of these tasks that it writes down in the transaction log, they're dated. So what I can do is something called time travel. So if I want to go back to a certain point in time, I can say, let me go back to task 2. And task 2, right, it says every step we've gone. So if I just follow the steps through task 1 up to task 2, it will go back to this state. So I can see what my database was like at any time. Even though, you know, the data there, I just go to the latest task to see the current state. And this is great because now I can go back in time. So this is what Delta does, this transaction log. It provides ACID functionality. So because of we're writing down everything that's happened and the transactions, it provides the same formality and the same functionality that databases can provide. It allows time travel, which is awesome. We can go back to any point. Because they're all timestamped, we can just say, I want this point in time or this date, see what it looked like. Really good for lineage and debugging, as you can imagine, because you can go back, see exactly what changed. And because of the Parquet format underneath, perfect at data optimization and it stores things really well. So optimizing Delta. Delta also has some additional optimization that it can do on top of just Parquet files. Now let's look at our big table here. We know that it's going to store, data like this because this is Parquet. So this is the first optimization just by using Parquet files. It goes from this big bit of information with lots of letters to a nice narrow bit of data with lots of less letters and lots less memory to use. So on top of that, let's look at this table. Now if we save this to Delta, you might split it out into different row groups such as this and save these into files. So because it saves as Parquet, these are our 3 files that it uses. Now what it does is if we query this and say we want to select all the sales with the sales number, these are the numbers, right? The first column is the names and then we have the sales, which are the numbers. We want to know whether sales is greater than 14. Now of course Parquet has this transaction log. So every time we add a file, not only does it say I'm adding file A, B, C or whatever, but it also goes through and it does some analysis on the columns and it writes down some data about the file you're adding. In this case, it's writing the min and max, and it writes the min and max of a lot of the columns in your file. So this, for example, the first one is going to say the min number is 9 and the max number is 12 in the sales column. The second will be 15 to 20. We can see this, right? The min and max of all the values in that column for that file. Now we say, I want to select where sales is greater than 14. An optimization it does is, well, I can see that I know the first file has sales between 9 and 12. So if I'm just trying to load all the data with the sales is greater than 14, I don't need to look at this file. Now if you imagine you have lots of files and really big data, skipping the files and skipping all the data you need to look in to find the answer, going to save a lot of time. So without having to open that and read the data, it can already know some of the information about the data in it. So this makes it really, really quick. Now you might ask, of course, well, what about the name column? So again, you can do this, right? Letters have a min and max. We have an alphabet, it's ordered. So I can see when the name starts with D. Let me see the name where it starts with D. So I can look, and D actually will only fall in this last file. And I'll look, it's not actually in that, but I know D is within between A and S. So I'm still going to look in that line and say, okay, there aren't any names beginning with D. But I only have to look in that one file because I know not to look in the others. So let's say another way, right? Imagine we have the same data, but how we've added, it's come out like this, right? By the time we've added data. So a lot of these are, when we add the data, it writes to this Parquet. And we can see here, we're going to say, let's select the sales where the sales are equal to 14. But in this specific version, you can see actually 14 falls within every single one of these files, right? 14 is between 9 and 15, 8 and 16, and so on. Just going to have to look at everything. So is there a way to make this better? Well, yes, there's some commands that we can do. And this is called zorder and optimize. So what we do is we run this command called zorder on the sales column. And now it's going to order it by the sales column. And it might internally optimize things and save things. So in this case, it's saved things in 3 different files like this. And what it's done though is we can see we've ordered on the sales column. And this is going to make it a lot easier, right, if we're looking at where sales equals 14. Because the first file has sales between 7 and 9. The second one has sales between 14 and 16. And the last one has 28 to 35. Because we've ordered by this column, this means it's going to be much more efficient and more likely to skip files. So this is called zorder and optimize. So engines series. So Apache Spark. What is this? So Apache Spark, imagine that we're running our computer and we're getting lots of data. But as data gets bigger and we get lots more data with all this AI, right? Eventually we're going to have a lot of data. And it's going to be way too much for our laptops or our machines to handle. So that's really what Spark comes in. So Spark is an engine, and you can send some queries to it. Right? I say, hey, I want to store some data, or I want to do some analysis, some machine learning, stuff like that. And instead of all running on a single machine, a VM or something like that, it actually says, well, I've got loads of different engines and I've got loads of different machines. So I'm going to split whatever you said into different tasks and optimize it and send them across. And this is the same with data. I can store them in lots of different locations. It doesn't have to be the same location. And this is really it under the hood, right? It's this engine though is very powerful because it knows which tasks are sent to where and it can compile them all back together. So it's just optimizing, it's distributing, it's called. So it distributes things across different computers and machines internally. So you said these queries, what can we send it? It actually supports a lot of different programming languages. It might be a little different or some certain packages. So we have something called PySpark, Spark SQL are very common. Scala and Java and R, and we can write different languages. So it's not just set to a certain language or a certain vendor. We can do lots of different ways to interact with it. And this is great because we have different things that it's really used for. So Spark SQL is great for data engineering, doing tables, stuff like that. It's really good at streaming because of the power bill we can stream. So when you get real-time data coming in, like sensors, stuff like that. It's also really good at machine learning because of the power. Machine learning takes a lot of computing power. And we also can do graph databases. If you don't know what these are, I wouldn't worry. But it does also handle it if you happen to understand them or know what they are. So, Spark, it's open source. It's not a specific vendor. It's not down to anyone who's great, which is why it's being really heavily used. It's good at large data processing. So we love lots and lots of data. Good at streaming, multi-language support. So I don't mean languages we speak, I mean programming languages such as Python and SQL. And I say replaces, it's set out to solve a lot of things that Hadoop and MapReduce, some issues that they would have. If you have never heard of this, don't worry. If you see these names, know what they are, right? And Spark's kind of a thing that now probably a lot of people are using over these. A lot of people still use them, but Spark's one of the newer ones. So what is KQL and Crusto? So KQL stands for Crusto Query Language. It's a bit similar to SQL in a way, how it's kind of written. It's used in a product when we talk about Azure called Azure Data Explorer. And what it is used for, it's good for exploring unstructured data as well as structured data, right? So it's a good way to write queries, we call them, against structured and unstructured data. And it's really good for streaming, kind of new and real-time data. So that's one of its key uses. What is analysis services? Analysis services previously used to run on these things called cubes. So if you hear the word cube in analysis services or Excel, Power BI, it's kind of what it means. It used to have these MDX queries before. Now, for a few years now, we have a newer way of storing things. It's called tabular. We call it the tabular data model. And this uses DAX queries. So DAX is how we talk to a tabular model. We can still use MDX on all of it as well, but now typically everyone uses DAX. So what is this tabular? So it has this engine beneath it, and it stores a lot of metadata in our tabular model. There's a couple of ways we can see this, and these have information like the different tables included in the models, measures, if you're familiar with DAX, these are KPIs and calculations, and then different things like security. So this is just a file really telling how the data interacts with each other. So let's look at Power BI. So what is a Power BI dataset? So Power BI dataset is split into two different things. We have the data and we have the metadata. So we look at metadata, and this is what our analysis services engine uses. So this is the analysis service, the engine that powers it. But this metadata is a file. We have a new way of viewing it called Timdal, or previously called Timsal. If you've never heard of these, don't worry. But included, it just has all the information about how we want our data to interact. All the code, such as, I want to sum my sales. How do we calculate that? Which column do we sum, right? And more complex. Lots of other things, such as securities and permissions and all of this. So this is just saved. There's no data in this. It's just saved the metadata on how these tables interact. And then we have another side, which is the actual data, right? And this is a compressed copy of data from whatever a system is. So in Power BI, we actually copy data from our source, maybe it's Excel or a SQL database. We copy it into Power BI. We compress it, right? It's a copy of the data. We might do some transformations. So this is the data loaded after those transformations in Power BI. This is only present in import mode. So this is what an import mode is. So what is direct query and import? Import and direct query, looking in import mode first. So we look in this yellow box in the middle. This is what's in a Power BI service. When we publish a report, it separates the report to a data set and the Power BI report. So this top brown box is the data set, which has the data and the metadata, and then we have probably some visuals. So data is copied from the source. Right? Complex ETLs and transformations can happen. And this data is stored in the Power BI service. So app.powerbi.com, it's all stored behind the scenes. It's stored for you. Then when a user looks at the report, this report gets the data directly from the data set. So it doesn't look at the source anymore. It's all the data is in Power BI service, and that's why it's really, really quick and really powerful. And this same data set, it can be connected to lots of different Power BI reports and Excel. So this one data set can be used across lots of different things as well. So what is direct query? Now you notice direct query is very similar, except in our data set, we don't have the data, we only have the metadata. So when a user looks at a report, they might look at a specific graph. Now this graph says, I need some data. So it asks the metadata. The metadata, the data set, knows what the data should look like. So it goes to the source, wherever the data comes from, and it directly gets the data in almost real time, which is sent back and loaded to the visual. Now you can imagine that this is quite slow, because every time you do a filter or change some data, it has to reload the visual, and it has to go back to your database, wherever the data lived before, and load that data directly. So direct query is good in some ways, but a lot of the time we don't want to use it because it's very slow. You can't do much things like transformations or complex calculations, because it has to do this on the fly. So let's look at Fabric. So what is Microsoft Fabric? So previously, imagine that we have some data from some different types of source systems. Now we have something called Data Factory. Data Factory is a tool that can just load data and copy data. So it's really good at saying, hey, I want this data, I want to copy it and put it somewhere else, for example. Where would it put it? We'll put it in a SQL database, what we call, this is ADLS, this is Azure Data Lake Storage. So it's a data lake on Azure. It's just for files and stuff. So the Data Factory will be able to copy it and put it in one of these systems. We also have things like Data Explorer, which can use KQL, Custom language, to look at data and really get it streaming. And then we might do other stuff, like this machine learning, and this red symbol here is Databricks, which is an external company to Microsoft, who work very closely with Microsoft. These are tools that people typically do machine learning on. And then we might load the data into Power BI and do data analytics. So what we actually have is a ton of different services, right? And these blue ones are available currently on Synapse, Azure Synapse, which is really just a platform where you host all these different. It's got a lot more of other stuff as well, but these are just some of the tools we can use in Synapse. Then at the bottom we have Power BI, which we load the data as well, and we have a tool called Databricks. So all these different things, and really what happens is people are stitching different things together. Now Microsoft understand that Power BI is a really nice product. So actually what's happened is that Power BI has absorbed all those other features. Now they're still in Synapse and they're still going to exist and you can still use Synapse. But in the Power BI now, in the UI and the website, the interface where you go to Power BI, it has all these other things available. And this is renamed as Fabric, so it's turned green and turned to Fabric. It can still connect to all these other things like Amazon and Databricks, right? And it works really well to connect to this. And then what it actually does though, what one of the big concepts of Fabric is that instead of all these different areas, it has this single storage, the data lake, Delta Lake, right? So it uses Delta Lake, this Delta format. And then this is actually the same storage for all the different services, which is one of its big things. So it has here this Microsoft Fabric. And really it has different options for data science, engineering, data factory for moving data, data engineering, data science, data warehouses, a SQL, real-time, Power BI. All of this uses the same storage called OneLake, which is Delta. We also have Data Activator on the end. I'm not going to go into that. It's a new service and it's for triggers and reacting to your data, right? Get out of this and we'll have a separate session on that because it's not out yet at the time of this recording. So what is OneLake? So OneLake is a way how Fabric stores data differently. Traditionally, if we look at tools, we might say we copy data maybe into databases. So the top is a source. We might get data from Excel files or from the internet. We copy it into a database, which is the next step. And the third step, which is the small database, we often make things called data marts. And these are really just subsections of the big data warehouse. We might have a data warehouse with all the company's data. And then finance might have a specialized unit. So they have a data mart. So the data is copied over. Then the data is imported into Power BI. So we can see the last step is copied into a Power BI data set. And then we have this flow. We also might use this flow, which is a data lake, right? Where we dump everything into a data lake, do medallion architecture to copy data across, and then import it into Power BI. But often we use things like Azure Data Lake Storage and Databricks for this layer. Often though as well, we'll also have a data mart on top. It's the same thing, right? We might have a really big data lake and we want specialized units. In reality, in bigger companies, they'll often do this, where they'll have both data lakes and data warehouses, both used for different purposes, both still have good purposes, both still needed, because one might be for data science, one might be for transactions, and there are lots of data marts. You'll notice though, every red square, this is the same data copied, right? Because the same data might end up in a data lake and a data warehouse. Things like customers will probably need them both. The data is copied again into different databases, into data marts, and copied into Power BI. This is exact copies of the same data. So, what Fabric is we have these different tools at the bottom, right? We have Spark, we have Power BI, and we have SQL. And these are all different languages that can interact with data. The storage, though, is all Delta Lake. And the idea is that we're not copying data. So it all uses the same copy of the data. We have one file, or maybe a medallion architecture might have some copies of the data inside the Delta Lake, but that is the same files that each of the different tools use. So instead of copying the data from tool to tool to tool, all of the different languages use the same lake, this Delta Lake underneath the surface. This Direct Lake. So in Direct Lake, when we look at specifically Power BI, it uses the Analysis Service Engine. An Analysis Services Engine uses a compressed columnar data store. This is how data is stored in Analysis Services in Power BI datasets. Now Delta uses Parquet. Parquet is also a compressed columnar data store. So if we look at our import mode, what Microsoft have figured out, what they could do, is say, hey, we have this metadata in the data. What if we kind of split this into two, right? And instead of having that copy of the data live in the Power BI service, This is actually going to live in the Delta Lake. So we have this process where data is copied into the Delta Lake, which is a very similar format to what analysis servers use anyway. And we only store the metadata, a bit like direct query mode. However, because we're not going back to a source system, it still has the performance of the import mode because the storage of the data is the same. It's the same format that was in analysis services. What happens? We just kind of load a bit of the data we need into the memory. Power BI uses it, kind of goes, so we can do everything on the fly. And the advantage of this, right, this data that's in the Delta Lake, this is the same copy of the data that all the other tools use, right? So Spark and our machine learning and our notebooks can use this. SQL, so at SQL people who build the data warehouses, they can also use this. And also all our Power BI people who are using Power BI, DAX and Power Query, they can use the same copy of the data